Hi everyone, my name is Brianne Davies-Morel. I'm an honours student at the University of Western Australia, and today I'll be discussing my thesis, Exploring Human-Computer Interaction in Ontologies, a case study. My supervisors for this project were Melinda Hodkiewicz, Tim French, and Caitlin Woods. In 2022, we're living in an age of smart buildings. Buildings that can automatically analyze their environment and make real-time adjustments to maximize comfort and minimize energy consumption. They're characterized as sensor-rich environments that generate vast amounts of data daily. For building managers, engineers, analysts, the goal is to leverage this data to make smarter decisions around the operation and management of buildings. In particular, there is a wealth of opportunity in developing applications that extend a building's intelligence. For example, applications focused on energy management, occupancy modeling, or prognostics. Unfortunately, working with building data is hard. Every building site is essentially a one-off. They each have their own proprietary naming conventions and data management practices. As an example, consider a situation where a sensor is measuring the temperature of water leaving a pump. In a building, sensors are represented by point labels, and a point label contains all the information you might want to know about that sensor, its location, the equipment it's relative to, what it's measuring, and so on. Essentially, building metadata. Here, we have an example of what the point label could look like for 3 different organizations. Without looking into the conventions of each site, it's difficult to make sense of the metadata. If you did manually parse each label, you would see that they are all describing the temperature of water leaving a pump, with varying levels of detail. 2 specify the location of the sensor, and another specifies that the water is leaving, whereas in others, this information is implicit. Such heterogeneity in the representation of data means that there's a lack of interoperability between buildings. Applications, like prognostics, built for one building based on that building's conventions are not portable or readily reusable for another. Particularly, this is a problem for vendors who work with a multitude of organizations and want to scale existing solutions. As such, there is a need for a single source of truth, a common and shared representation of building metadata to act as an interoperability standard. In the building industry, ontologies have been used for this purpose. An ontology is a model that defines a common vocabulary for a group of people needing to share representations about a domain. It includes machine-readable definitions of concepts and the relationships between them. Such a model would provide semantic descriptions of all the things in a building: equipment, like a pump, points, such as sensors, locations, such as rooms. At this point, you might be wondering what the difference is between an ontology and a taxonomy. An ontology is in part a taxonomy. It can structure the information according to the high-level categories that they belong to. So, for example, a building ontology would specify that a water pump is just a type of pump, which is a type of HVAC equipment, and that a water temperature sensor is a type of temperature sensor, which is most generally just a sensor. However, a taxonomy fails to describe the relationships between separate categories. For example, the relationship between a pump and a temperature sensor, whereas an ontology can. An ontology extends the dimensionality of the model by allowing you to specify that a pump has a temperature sensor, that it has a certain location, which is contained within another location, and so on. These relationships provide the rich contextual information necessary for building applications. The value of abstracting the domain like this is that you no longer need knowledge of site-specific naming conventions to query a building. Thinking back to our previous example, say an engineer wanted to know what the temperature is leaving a particular pump. Traditionally, they would need to know the point label representation to query a database or a building management system. With an ontology, however, the engineer can formulate the query using natural language. For example, what is the temperature leaving pump XYZ? Behind the scenes, the ontology is mapped to the building's data and retrieves the value for the engineer. The engineer never needed to know what the data looked like, so the same query would work for building 2 and building 3. Thinking along the same line, if an application was built based on the ontology, it would then be portable between buildings. But for an ontology to be successful, it is imperative that it is usable and understood by the end users. A building ontology, for example, should contain all the information an engineer needs to perform day-to-day operations, as well as represent this information in a way that the engineer understands. However, research suggests that ontologies are often inaccessible and incomprehensible to their end users, and this has been recognized as a barrier to the uptake of ontologies by real users outside of academia. In other software fields, usability is usually corroborated by the involvement of users throughout the design process. However, users are rarely considered in ontology design or evaluation, and even when they are, there is no documented process on which techniques work to engage them for a successful evaluation. To address this gap, my project explored human-computer interaction in ontologies through a case study on user evaluation. The study centered around the evaluation of an existing open-source building ontology. Brick aims to address the heterogeneity in the building industry, which we discussed earlier, by providing a standardized cross-vendor representation of buildings. It is a collaboration between academic researchers at UC Berkeley and UCLA. It is supported by Johnson Controls and has been used at companies such as Schneider and Carrier. The users of Brick are technical professionals working with building data, such as building managers, engineers, analysts. Brick was chosen for this case study as it presented an ideal opportunity to ascertain the value of user involvement in ontology development. It is an ongoing project, but has never actually been evaluated by the users. The study consisted of 5 stages. Before conducting user evaluation, it was crucial to develop a strong understanding of the ontology and its development. As such, the first stage included reviewing publications relating to the ontology, documentation, and code. Once familiar with the general schema of Brick, the ontology was implemented for an existing HVAC system to provide further familiarity and identify any potential gaps. Data was provided through collaboration with an international pump manufacturer, and the output was a Brick model. In the third and the fourth stage, the evaluation design was conceptualized and then implemented. Finally, the collected data was analysed using thematic coding techniques. In this presentation, I will focus particularly on the evaluation design and implementation. Semi-structured individual interviews were chosen as the primary format to conduct user evaluation. This format allowed for detailed feedback to be gathered on the metadata within the ontology, but also enabled for open discussion on the participants' work requirements and potential use cases. Each interview was an hour long and held with potential users of the Brick ontology. Prior to recruitment, the project was submitted to UWA's Ethics Committee, and once approved, 4 participants were recruited across 2 organisations. They were convenience sampled and contacted by email, where they were provided with a participant information form and consent form. Each participant had 20+ years of experience in the building industry, and none had prior experience with Brick or ontology modelling. Each interview contained 4 stages, beginning with a discussion of the participant's background and experience with buildings. The purpose of this stage was to identify the perspective of the participant and the information they may require from a building ontology. The requirements expressed were later analysed against the capabilities of Brick. In the second and third stage, participants were guided to directly review Brick, and in the fourth, a survey was administered. As mentioned earlier, there has been little research on the best way to perform user evaluation of ontologies, and this includes the presentation of the model. To explore this, the ontology was presented using a variety of visualization techniques throughout the interviews. In the second stage, participants were first introduced to Brick using a condensed on-paper version. They were shown the categories of information. Here, for example, we have the class HVAC equipment shown as a taxonomy. A taxonomic structure was chosen as it is a way of formulating information that most people are familiar with. The model was initially condensed as to not overwhelm participants while still being able to indicate the overall structure. Once participants had reviewed the categories within BRIC, concept maps were then used to illustrate the main relationships. As evident here, the relationships were grounded in examples of their use to ensure that they weren't too abstract for participants to grasp. Next, after reviewing the on-paper graphics, participants were given the opportunity to explore BRIC in full. To accommodate a complete view of the model, it was presented as a web-based list, making it clickable and expandable. Again, being a taxonomy, it served to evaluate the categories of information only. So here we have the first view, the classes, and then the view if a participant were to expand the class point, and so on. Throughout the review of BRIC, 3 standard design criteria were evaluated. The first one was completeness. For this, participants were asked to consider whether the model contains all the information they would need in their day-to-day job. The second was expressiveness, which relates to the model's ability to represent the relationships between all the things in a building. For this, participants were prompted to examine if there are any relationships between classes that they would need for their building applications or that they think were missing. If they demonstrated confusion with the current relationships, they were asked to describe the connection in their own words. The final metric was usability. Does BRIC represent information in a way that is easy to understand and use? For this, participants were asked about the naming and structuring of information. Finally, the interviews concluded with a survey based on the system usability scale, an industry standard for measuring the perceived usefulness of a system or product. It consisted of 10 questions concerning the participants' experience with the ontology. For example, I think that I would like to use this ontology frequently. The responses were rated on a 5-point Likert scale and later summarized into a singular score. The findings of this study served to provide both a user assessment of BRIC and also report learnings on using human-computer interaction techniques to evaluate an ontology. In terms of BRIC findings, the evaluation process revealed that the ontology does indeed address a prominent issue in the building industry. For one, participants recognized the lack of interoperability, stating that companies have their own proprietary products, different programming languages, protocols. They also demonstrated frustration with the current state of building data, saying that point labels are nuts. Sometimes you get them out, and even when we read them, we go, I don't even know what that is. The interview process was also effective at reviewing the completeness and usability of BRIC. Overall, participants were satisfied with the scope provided by the main classes, but found that at a detailed level, the model was not complete, as 34 concepts were indicated as missing. Participants also disagreed with the naming and the structuring of information, with 10 suggested to be reclassified and 6 suggested to be renamed. On the other hand, the process did not yield any significant findings on the expressivity of BRIC. While the purpose of the concept maps were to ground the otherwise abstract relationships, participants were distracted by the examples. Consider the following concept map, the prompt where a few relationships were introduced to participants, one of which being feeds, which describes the topology of the building by indicating a sequential process between 2 pieces of equipment. For example, you could have chiller feeds cooling tower. When introduced to this map, participants took to discussing the system topology over the relationship itself. For example, one participant observed you could put these in a different order because the cooling towers should kind of be related to the condenser. While this meant that there was no significant findings on the expressivity, it did lead to an interesting discussion around how participants intuitively thought about buildings. These intuitions ultimately become design choices when modelling a domain and were one of the ambiguities in the BRIC ontology identified when attempting to implement it with a pump manufacturer's data. For example, there was no guidance on how to model the topology of HVAC systems and whether this would affect the description of sensors that are relevant to a particular equipment side. Without recommendations, this sort of thing has to be decided case by case, depending on the perspective of a modeler, which does defeat the purpose of having a common representation. The presentation of the model, whether on paper or web-based, had a strong impact on the participants' understanding and type of feedback generated. The on-paper graphs prompted high-level discussion regarding building systems and user requirements. Participants were keen to sketch out their own understanding of the system and make modifications to the given graphics when they disagreed. One downside, the condensed nature of the on-paper graphs caused misinterpretation of the model at times. For example, all participants cited pump as missing when it was just excluded from the short version. This did cause discussions to be sidetracked at multiple points throughout the interview. In comparison, the web-based format was better for focused feedback on individual metadata, particularly in regards to completeness and naming. The expandable nature of the list helped participants to navigate through more of the ontology, but it's worth noting that no participant explored it in its entirety due to time constraints. The difference in the type of feedback, one being brainstorm-like and the other being task-focused, suggests that the two techniques would be better for different stages in an ontology's development. The on-paper concept maps and taxonomies would work well to prompt participants to discuss their requirements at the beginning of the design cycle, as well as extract natural intuitions about the domain. A fully formed ontology would be better evaluated as an expandable and complete list, with an additional option to search the list in cases where participants believe something is missing. The survey revealed that the model's perceived usability is low, with 3 out of 4 participants achieving a score below the industry average of 68. Verbally, participants indicated a similar perception of usability, saying that it was an okay first pass, but it needs some work. One participant noted that your naming convention worries me because I don't think that most people would know what some of those things are. And another, your relationships and terminology isn't quite what I would do. While administering the survey, it was also suggested that the interview process was not sufficiently immersive and that the quality of feedback would improve with exposure. One participant noted that it was very hard to answer some of the questions, having just an hour and a half on it. And another stressed, there's a gap in my understanding of some things, but that usually comes about with more use. This suggests that the interview process was not sufficiently immersive. Indeed, none of the participants explored the web-based list in full. As a solution, one participant suggested maybe a second interview, and another recommended that it would have been good to read the definitions for each of the key headings, but later amended that I definitely wouldn't do this though because I wouldn't have time. These conflicting statements illustrate an expected challenge in conducting user evaluation of an ontology, how to balance the quality of feedback with time considerations. On one hand, the results suggest that it is not feasible to provide a complete overview of an ontology within a single 1-hour interview, especially when participants are unfamiliar with conceptual modelling. However, extending the length of an interview makes for a time-consuming commitment. As suggested by a participant, one solution is to conduct multiple rounds of interviews. In particular, it would make sense for user evaluation to be performed earlier in an ontology's life cycle so that multiple rounds of feedback are possible. That way, the ontology engineer's understanding of the domain and the complexity of the ontology grows alongside the participant's familiarity. Overall, there are 3 main lessons from this study that ontology engineers can keep in mind for their own practices. First and foremost, user evaluation has the potential to generate valuable feedback and find gaps that traditional ontology evaluation cannot. It goes beyond gathering a list of vocabulary, which can just be done by reviewing a textbook or a building management system, and provides ontology developers with the opportunity to capture and formalize the natural intuitions and language of users. Secondly, the presentation of the ontology influences the participants' understanding and type of feedback generated. With that in mind, it's recommended that different techniques, different visualizations would be good for different stages of a model's life cycle. And finally, user evaluation is time-consuming, but the quality of feedback will improve with exposure. A solution is to follow a traditional user-centered design process where users are involved from the get-go and there are multiple points at which they can give feedback. Of course, the study was not without limitations. Due to time constraints, the participant cohort was small and homogeneous, with all 4 participants being engineers working within Western Australia. Similarly, the evaluation was focused specifically in the building domain. Future studies would benefit from a larger number of participants with varying demographics and from different domains to confirm if the findings are representative of the wider population. Thirdly, the evaluation was of a fully formed ontology. And so the question remains, what does evaluation look like at an earlier stage? And can the findings here be applied? And finally, the study focused on engaging users with a subset of ontological concepts, classes, and relationships. Other concepts, such as rules and properties, have yet to see a user-based design or evaluation. Although the methods presented here need to be further tested, the study provides valuable and detailed reports of user interaction with ontologies. Ontology engineers can use the study to understand the effort, benefit, and limitations of a user-based evaluation, as well as guide their own development methodologies. Thank you very much for listening.